Let's go ahead and screen capture. Alright, hope everybody is doing well. Let's go over any questions you have. So we're going to go through most of the material you need for the homework today. We've talked about flip-flops, so you should be able to have made a start on the first few homework questions. But most of that material we're going to go through this afternoon. Lab, I'm hoping people are making progress on. So any questions, go for it.
Hey, I was just wondering how to draw the 7-segment display on the wiring diagram. How do you want that drawn?
Okay, so you can draw that. The main thing I want to see is the connections. So, I mean, you can just draw a box, and you can label it, or you can draw, you know, a 7-segment display inside. But the inputs to that, I think, are labeled A, B, C, D, E, F, G. Right, so just draw the wires that go to each of those. And they don't have to be in order. If you have a wire coming down here, you could put G down there instead, and so on.
Alright, thanks.
Let's see, checkerboard with K-maps. So you have an option. Let's say you end up with something like this. Let's say this is A, B, and C. Alright, you can do 1-by-1 covers, right? So you can do this as a product of sums, and the K-map doesn't buy you anything, right? It's just A bar, B bar, C, or A bar, B, C bar, or A, B, C, or A, B bar, C bar. But there is a trick you can use, okay? So let's look at two variables, A, B, and let's suppose we have a K-map like this. Okay, so we know that this would be A bar B or A B bar, right? And that corresponds to the truth table like this. So 0, 1, and 1, 0 are 1. Well, that is the truth table for A exclusive OR B. Okay, so here's the thing to do. Make yourself a truth table with A, B, C, and make a truth table make an output column for A exclusive OR B, exclusive ORed with C. And see what you come up with. And you'll see that you probably come up with this truth table. Okay? In which case, if you have exactly this, you can just do A XOR B XOR C. If it's reversed, if you have ones here and here and here and here, then it would be the inverse of A XOR B XOR C. And if you want to build that in a circuit, right, here's A and B. They go into an exclusive OR. And here's C, and that goes into an exclusive OR with the XOR of AB. The output is A XOR B XOR C. And the parentheses don't matter. You can do these and then XOR with A, or the other way around. So checkerboards, think XORs, make yourself a truth table, see if it matches the truth table that you're trying to build. Alright, other questions? That probably sounds really weird on the microphone. But if you got a 4 variable where the whole thing isn't checkered, well, where do you have a 4 variable? I'm just curious. Because if you're doing a full adder, you've got 3 variables. If you're doing the original truth table, then you would have 4 input variables. But if part of it is checkered, I mean, since you're probably not building directly from that 4 input truth table, I would just go ahead and write it as a regular sum of products. And if you have, isolated ones, just cover them with a 1 by 1 rectangle. But what you can do is, and this, is a little bit outside our scope, but if you spend a lot of time playing with K-maps, you start to be able to bend the rules a little bit. So let's say I have a little checkerboard sitting right here. Okay. Or let's make it a little bigger. Make it worth our while. Let's say I have this, this 4 by 2 checkerboard sitting in the middle, but that pattern doesn't hold elsewhere. All right, I've got this kind of stuff. I have a checkerboard pattern in the case where C and D are both 0 or C and D are 1, 0. So I could actually represent this by, if I'm in this column where C is 0 and D is 0, or I'm in this column where C is 1 and D is 0, then I could AND that with whatever this XOR turns out to be. I think it's A XOR B XOR, it looks like C. Right? But that's more trouble than it's worth, because like I say, the only case I think where you're dealing with a K-map with 4 input variables is if you're trying to simplify that original truth table for 4 bits in, 3 bits out. And for that, you're not going to reduce that to an actual circuit, so I would just do a product of sums, 1 by 1 rectangle for these, and then, cover the rest of the stuff however. Actually, this one you could do like that. This one you could do like that. But there are things you can do with XORs, but mostly we use them if it's just, just a straight checkerboard. All right, what else? So I want to remind people that your midterm exam is on Tuesday. Okay, that's our next class. I'll start a few minutes after 12 just in case people come late. And it'll be a 50-minute exam. And we'll plan on a lecture afterwards during which we can either talk about the questions on the exam or we can go on to other material. And you'll want to have a way to take pictures of answers, and you're probably going to want to write your answers on paper, take a picture, upload that to Canvas for some of these questions. Some of these questions may be short answer. They may ask you to type in an equation or, analyze a circuit and answer questions about it or something, but there may be some where you need to, draw a K-map or something like that. So try to have a way to be able to take pictures of this and upload those pictures to Canvas. Okay, this will be experimental. I've not done a 250 online exam before. Most of my classes are programming courses, so people are writing code, and that's pretty easy to do in Canvas. I did a discrete structures final last quarter, and that involved, some drawing of pictures, but not too much. But this is going to be, most of the homework problems you're doing, it's just page after page of circuit diagrams, truth tables, system diagrams, things like that. So you don't want to try to use software to create those things, right? Your best bet's going to be write on paper, take a picture, upload the picture. So if you have concerns about that, try to let me know today, okay, so we can figure out what's going to work best for taking the exam. All right, no other questions?
Is the exam going to be the length of the class time?
No, it's going to be 50 minutes, and then we'll lecture afterwards.
Okay.
I have not written it yet, so I don't know how many questions. But some of the questions will be shorter than others, right? Some of them may say, you know, write a truth table for a circuit that does this. Some of them may be, you know, take this equation, simplify it, and write a minimized product of sums using K-maps. That's going to take longer. Some of them may be, here's a fuse map, write the equation of, you know, output F2 based on the inputs by looking at the fuse map. And that one would be pretty straightforward. Yes, so I mean that is an issue. My suggestion would be, so I'll post a practice exam later on that doesn't actually have any questions, but just to give you a place where you can practice uploading stuff. And so my suggestion would be, you know, pretend you're taking the exam, draw a figure on a piece of paper, try to take a picture and upload it to Canvas and see how long that takes. I will take that into account, but I don't want it to be, you know, something that takes the majority of your time is trying to upload these things. As long as you have, you know, a clean picture that I can read, I'm not worried about cropping. I'm not too worried about neatness, within reason, right? Try to be as neat as you would write something. 5 minutes to upload some photos. Is that upload time you're looking at? Or is that time to, like, you know, get the software, get the picture to come out sharp, things like that? If it's upload time, I'd say reduce your resolution. Because some of the photos I'm getting from people are extremely high resolution, and they don't need to be that high. Again, if you have a good tool in your suite like OrphanView or, you know, any of the Linux tools, it's pretty easy to resize and rescale those once you know how to do it, right? So it's something to get familiar with ahead of time. And I will be on Zoom during the exam, okay? I'll have chat disabled among students, but you'll be able to chat with me. If you're running into issues, right, we can talk about it at the time. And if you're not sure how to do this, catch me during office hours, right? I still have office hours tomorrow morning. That's the last for the week. But then Monday morning and Tuesday morning and Tuesday at 11. Tuesday at 11 is cutting it pretty close. But you know, catch me sooner rather than later, and we can screen share and we can go over, you know, whatever tools you're using, see if there's a way to cut the size down to do a faster upload or whatever. But definitely, you know, do some prep so that you have an idea how you're going to do that. And like I say, I'll open a practice quiz that'll have an upload area later on today. Yeah, you're welcome. All right, anything else? So let's continue talking about sequential circuits. So I introduced the concept of a state machine at the very end of class on Tuesday, just to put it out there and get it in your heads. But let's go back and review our flip-flops. Okay, these are our storage elements, and we've got basically a few kinds of flip-flops. We have a D flip-flop, and so there's an input. And there's always a clock. Okay, and the clock is shown with a little notch symbol on it. That means that it's edge triggered. Okay, it doesn't matter if the clock is high or low. In this case, it matters when the clock changes from high to low. And there's a Q output, and there's usually a Q complemented output for free. And so this device we can describe as follows. So here's D. Here I can write Q plus or sometimes Q star. This is the new value of Q after the clock ticks. Okay, so this is Q after the clock goes through this rising edge. And if D is 0, our output is 0. And if D is 1, our output is 1. Okay, so that's a D flip-flop. The book has SR flip-flops. I don't usually do a lot with them, but 2 inputs S and R, there's the clock as usual, and the Q output, and the Q bar output. And this looks like this. Okay, so if S and R are 0, then Q plus is equal to Q, which just means, you know, Q before, right before the clock ticks. So if S and R are both 0 right before the clock ticks, Q does not change. But if S and R are 0, 1, then after the clock tick, Q is 0. If S and R are 1, 0, then after the clock tick, Q is 1. And 1, 1 is forbidden or undefined usually. We assume the person using this device will not set both S and R to 1 when the clock ticks. There's a toggle flip-flop, which looks like this. And its function table looks as follows. If T is 0, Q does not change. If T is 1, Q complements or toggles. So if I set the T input to 1, every time the clock ticks, the Q output flips. If it's a 1, it'll flip to a 0. The next time it'll flip back to a 1. And then these two kind of get combined into what's called a JK flip-flop. And this is probably the most popular, most general purpose flip-flop. And it looks almost like a set reset, except we make use of this forbidden state. So if both inputs are 0, the output's unchanged. 0, 1 is a reset, 1, 0 is a set, 1, 1 is a toggle. Okay, so there's the four things, the four types of flip-flops we mostly deal with. And practically speaking, this one and this one are kind of the most useful, right? If you have this, you get a toggle for free. Just set J and K to 1, or tie them together, and it acts like a toggle flip-flop. I simulated one of the homework circuits, and when both inputs were on, the output flashed on and off rapidly. Yeah, so that's probably an undefined state or a forbidden state. Sometimes that can come from what's called a race condition, right, which we looked at a little bit, where if the inputs change at just the wrong time, you can get an output that's unstable. In reality, for an SR, depending on how it's built, it'll either give you a 0 or a 1 in this state, usually. But for some of the other homework circuits, yeah, you could get that undefined state. That's probably what you were seeing. That's cool to know that Tinkercad will do that. Alright, so I'll keep those handy. But let's look at state machines. It was the circuit simulator on the NGRCS website. Oh, okay, yeah, that I believe. But Tinkercad may do that too. Alright, so what is a state machine? It's a system with memory, which we call, memory holds what we call the state of the system. It's a bunch of flip-flops. There's combinational logic. So ands, ors, nots, XORs, things like that. there's inputs and there's outputs. But there's also feedback. And it's the feedback that really makes it a sequential circuit, a state machine. Okay? So we can draw a very general picture of this. Make sure I'm recording all of this. Yep. So we can draw a very general picture of this. So let's draw a memory block. This is a set of flip-flops. Let's draw some combinational logic. Let's have our inputs going into the combinational logic. Let's have our state going into the combinational logic. And a set of outputs from the combinational logic feed the inputs to those flip-flops. And something from here generates outputs. And there's a clock. Okay, probably the most general state machine picture here. So combinational logic, bunch of flip-flops. Their inputs are fed from the output of this combinational logic. The output of the flip-flops, the Qs and the Q bars, feed into the combinational logic. And there's inputs that come in here from the outside world, and there's outputs that go to the outside world. And there's a clock which drives all of the clocks on those flip-flops. And you can build any modern computer with this circuit, right? The combinational logic gets fiercely complex. It can have literally billions of gates to it, okay? And the state, the flip-flops that hold ones and zeros, there could be, 16 billion of those. If you have 16 gig of main memory, it could be, a few trillion if you consider that your hard drive contains information that affects the state of this system. So these are really big boxes, right? But this is the basic setup. And it's all driven by this clock. And the way we're picturing this, every time that the clock ticks, every time it goes from a 0 to a 1, whatever the inputs to the flip-flops are, get loaded into the flip-flops, right? This clock line goes high, and the output changes based on, what the inputs are and maybe what the current value of the flip-flop is. All of these flip-flops get loaded, all of their Q outputs change, and that feeds all of these new ones and zeros into this combinational logic. And they work their way through here, they bubble across, it creaks and groans, and eventually, outputs come out to the outside world, but outputs also come out here and go back to these inputs to your flip-flops. Right here, right here, right here. But because the clock has already ticked, those inputs are ignored. Which means all the time it takes for signals to come through here, all the propagation delays, the race conditions, the glitches, none of those matter. Because while all that stuff is percolating, and you've got different values coming out here, they're going to the inputs of your flip-flops, but they're being ignored. Why? Because the clock is already high. And then, some eons later, a fraction of a nanosecond, eons to a transistor, the clock drops, and still nothing changes. But then eventually the clock will tick upward again, and when that happens, all of the inputs that you've set up here, now those modify the outputs. And once those modify, this line of values changes, the inputs to the combinational logic change, and the whole thing happens again. And while all of this is happening, the inputs from the outside world, the push buttons, the sensors, whatever is feeding this, can be changing. And those inputs can change the inputs to combinational logic, which might cause the outputs to change, or it might not. Okay? but those will probably cause these outputs to change, which have no effect until the clock ticks. And there's two types of state machines, two categories, Mealy machines and Moore machines, and we'll talk about them in a little bit, but basically the distinction is, can these outputs change as soon as the inputs change, or do the outputs only change when the clock changes? Okay, so we'll go into those definitions a little later. But this is our basic setup, okay? And our goal today and the rest of this week and up through the first homework, which is due on Wednesday, is to be able to take a state machine and analyze it and figure out what this machine does. Okay, and then the following, so this is chapter 4 in the text. The following unit, which is chapter 5, we're going to look at synthesis. We're going to do the opposite direction. We're going to say, I want a machine that does this. How do I build it? And we'll figure out what the combinational logic looks like, what kind of flip-flops, how many flip-flops, and how everything should be connected. Okay, synthesis is trickier than analysis, but understanding how to analyze these will help us when we get around to trying to actually synthesize, try to come up with these circuits. And let me give you a heads up here. This is a major departure from where a lot of other courses take us. Okay, a lot of courses that we do are very procedural. Okay, you learn how to solve an equation of a certain type. We're given the quadratic equation, and now if we're told, ax squared plus bx plus c equals 0, we can say x equals negative b plus or minus squared b squared minus 4ac over 2a, that thing that we learn as an incantation, right? Or we're given a circuit with resistors in it in Engineering 120, and we want to find the current going through a wire. And we learn this procedure called KVL or KCL. And it's hard, right? But it's a fixed set of steps. You follow these steps and you get there. Okay? Synthesis is different. Synthesis is where we're starting with nothing and we're trying to create something. And it's a fundamentally harder task. And it's, in my experience, it's why physics is such a difficult course for most engineering students. It's why a lot of programming gets very challenging. It's why digital design gets very challenging. Okay? Because analysis, we've got everything here, we have to break it down and study it. Synthesis, we're really starting with none of this and we're trying to create it. And you're already doing some of this when you're coming up with wiring diagrams, right? You're going from nothing to a truth table, to equations, to a wiring diagram. So this is going to continue that trend. And synthesis is going to be challenging, okay? But for the next week, we're doing analysis. But you want to learn this part well because it will help when we're trying to synthesize these circuits. All right, so I'm going to make a fairly random state machine. And I'm going to label my inputs and outputs on this first flip-flop D0, Q0, Q0 bar. And on this next one, I'm going to label them D1, Q1, Q1 bar. And if I had another, I would label with a 2 and so on and so forth. Okay, all of my flip-flops are going to be clocked together. And this is kind of a cardinal rule of synchronous design. Your clocks all just get fed from one clock input. Alright, and I'm going to make some random combinational logic. I just lost my second Zoom session. There we go. Let's make some random combinational logic. So I'll take Q0 and Q1 bar, and I will AND those, and I will take Q1 and Q0, and I will OR those, and I don't know, I'll feed this back to D0, and I'll feed this to D1. this may be a totally ridiculous circuit. It's intentionally completely random. Okay, so someone comes up to you on the street, hands you the circuit, says, tell me what this does. I'll give you $1. Okay, how do you do this? It's the exact same procedure every time. Okay, but it's a lot of steps. So we'll go through this and work through these steps, and then we'll do this again and again, and then in the homework questions you'll do this a bunch of times. Okay, and it will get easier and it will get faster. But the first few times it's a pretty slow, painstaking process. Let me make an output here also. I'll call this my output. I should have an input somewhere too. I'll make an input X, which comes into this OR gate. Alright, so that's a connection, that's a connection. All these other wires are just crossing over, they're not connected. And our question is, what does this do? Alright, so set of steps. First step, 1, write equations for the flip-flop inputs and the state machine outputs. Okay. We're going to take this and we're going to turn it into a set of equations. And once we have equations, then we can forget about the figure and we can just do, Engineering 250 style analysis. Okay, so write equations for the state machine inputs. Okay, so D0 is one of the inputs. Okay, the clock is not considered an input. The clock is uninteresting to us at this point because the clock simply drives the clocks on each flip-flop. So don't think of the clock as an input. If you have a D flip-flop, the input is D. If you have a JK flip-flop, the input is J and K, S and R, T. Okay, so we look at the circuit and we say something like D0 equals, well, where does D0 come from? It's the output of an OR gate. Okay, so it's the OR of X ORed with this line right here, which is Q1 bar, ORed with this line right here, which is Q1. Well, I made a silly circuit. Alright, so why is that a silly circuit? Because Q1 bar ORed with Q1 is always going to be 1. So let me just get rid of this input. Alright, so this is a 2-input OR gate. So D0 is the OR of X and Q1. Alright, so we'll keep it kind of interesting. So X ORed with Q1. D1 down here comes out of this AND gate, and this AND gate is Q0 ANDed with Q1 bar. So D1 is Q0, Q1 bar. Our output Z is also the output of that AND gate, Q0 ANDed with Q1 bar. Alright. And now we've got 3 equations that describe the flip-flop inputs and the output from the state machine. And obviously if you have more flip-flops or you have more inputs on each one, you're going to have more equations. If you have more outputs, you're going to have more outputs over here. But we've captured the essence of this with a series of equations. Okay, I'm going to put the picture of the circuit aside for now. We're going to go on to step 2. Make a table which shows present state and next state. Okay, so what is the state? This is the combination of flip-flop values. Okay, I'm going to go to a new sheet of paper. I'm going to sharpen my pencil. And these tables get pretty wide. Okay, you'll get a feel for it over time. But I'm going to leave myself lots of space. Alright, the present state of the machine is the value of Q0 and Q1. Okay, it's the value of these two flip-flops. So I'm going to, let's say, input, present state, next state, output. We're going to have 4 areas to this table. Okay, so I'm going to have my input X. That's my input. I'm going to have my present state, which is going to be Q1 and Q0. Okay, so this is the state of my machine, and this is the input to my machine. And it's 3 binary variables, so I have 8 possible combinations. Alright, and I know I draw sloppy horizontal things, so I'm going to mark these into groups of 2. What I want to do is I want to make a column for the output Z. Okay, well that's pretty easy. It's just Q0 ANDed with Q1 bar. And then I want to make columns for D0 and D1. Okay, so let's do this. Let's do output Z, which is Q0, Q1 bar. Now you may want to, make a separate column for Q1 bar so that you can just AND it with Q0. But this is relatively simple to do in our heads after we've done enough AND operations. So I'm just going to take Q0 and AND it with Q1 bar. Well, if Q0 is a 0, I know the AND is going to be a 0. So all of these are 0. And if Q0 is a 1, I need Q1 bar to be a 1, which means Q1 has to be a 0. So it's the 0, 1 that's going to give my output a 1 value. And 1, 1, Q1 bar is going to be a 0, ANDed with 1 will be a 0. So do an extra column or work offline or something, but convince yourself what the output is and fill in a column for the output variable. And now I'm going to make a column for D1. And D1 is also Q0 ANDed with Q1. Well, I already calculated that, right? So I can just copy from my output to D1. Only in this case, right? Because this happens to be exactly the same equation. But in general, it's going to be something different. And you gotta speak up if you get lost or confused with what the heck I'm doing here, because it doesn't get any clearer. Alright, let's make a column for D0. And D0 is X ORed with Q1. So I'm going to look at X. Anytime that X is 1, D0 is going to be 1. And anytime that Q1 is 1, D0 is going to be 1. And everywhere else, X is 0, Q1 is 0, that's going to be a 0. Alright, here comes the kind of magic part. D1 and D0, these are inputs to what? D flip-flops. Right? And we know that when you have an input to a D flip-flop and the clock ticks, something happens to the output. For a D flip-flop, the output becomes whatever the value of the D input was. So I'm going to make a column. I'm going to call it Q1 plus, and I'm going to label this next state. And what I'm going to put in here is what's the value of Q1 after the clock ticks, right? Because we have this clock going into our flip-flops. At some point the clock will tick. What's the value of Q1 going to be? Well, it depends on the value of D1. For a D flip-flop, it's a really easy translation. The new value of Q is whatever the value of D is. 0 becomes a 0, 1 becomes a 1. So here again, in this particular case, because I have a D flip-flop, my Q1 value is going to be a repeat of the D1 column. Okay? If my input is 0 and my present state is 0, 0, I've calculated that D1 is going to be a 0. Which means that when the clock ticks, since my D input's a 0, Q is going to be a 0. So my new value of Q here is going to be 0. But if my input is 0 and my present state is 0, 1, I've calculated, I've analyzed that my D1 input is going to be a 1. In other words, all of this logic is going to combine, and I'm going to end up with a 1 coming into this D1 input. That's in this case. Well, if my D input is a 1, when the clock ticks, my output becomes a 1. Yeah, you can write this as a formula. D1 equals Q0 ANDed with Q1 bar. Right, yeah. Alright, so we can do this in all cases. And like I say, for a D flip-flop, the new value of Q after the clock tick is just whatever the D input is. So D flip-flops make your life a little easier because the Q output matches the D input. D0 equals XOR Q1, right. Hopefully that's what I did. Alright, we have another flip-flop whose output is Q0, and that's also a D flip-flop, and so after a clock tick, the value of Q0 will be whatever the value of the input D0 was, right? And so if D0 is a 0 after the clock tick, Q0 will be a 0. If D0 is a 1, then after the clock tick, Q0 will be a 1. Okay, and this is our complete state transition table. And what does this mean? Well, we can kind of ignore this middle part, right? And we can basically say if this is our present state and this is our input, this will be the output, this will be the next stage. If this is our present state and this is our input, this will be the output, this will be the next stage. Let's see, the next state variable kind of confuses me. This is just looking at what a D flip-flop does. Okay, so let's just look at this column right here, Q1 plus. It's this column from the table that describes a D flip-flop. If, based on whatever is happening over here, we know that D1 is a 1, then we know that after the clock ticks on that flip-flop, its output is going to be 1. And if whatever is happening over here causes D1, the input of that flip-flop, to be a 0, then we know that after the clock ticks, the output of the flip-flop will be a 0. Okay, so this is just showing what the flip-flop's output will be based on its input. So does the output change with the next state? Well, the output we calculated here, right? And you can see that when we're in state 0, the output is 0. Here it looks like the output's always 0 except in state 0, 1, right? So yeah, so what is this thing going to do? Let's suppose that we start off in state 0 with an input of 0. When we tick the clock, the output's going to be 0. What's going to happen? The next state is still 0. Yeah, it's kind of like a timing diagram. So if we're in state 0 and we tick the clock, our next state's going to be 0. We're just going to stay in state 0 forever. But if we're in state 0 and we raise our input to a 1, the next time the clock ticks, we're going to go to state 0, 1. And if we're in state 0, 1 and our input is still a 1 and the clock ticks again, we're going to go to state 1, 1. And if we're in state 1, 1 with our input 1 and the clock ticks again, we're going to go back to state 0, 1. And if we're in 0, 1 with an input of 1 and the clock ticks, we'll go back to state 1, 1. So if the input is 1, we're going to eventually end up in state 0, 1, and we're going to bounce between that and state 1, 1 each time the clock ticks. And each time we're in state 0, 1, our output's going to be a 1. And when we go to state 1, 1, our output's going to be a 0. So that's what happens if we start in state 0 and our input is a 1. But if we start in state 1 and our input is a 1, what happens? Or if we start in state 1 and our input is a 0, what happens? So this table has all that information for us, but we want to change it into a different format. Okay, we want to summarize this analysis that we're doing in a very kind of long-winded ad hoc manner. So let me show you what a summarized version of this would look like, and then we'll take a break, and then we'll come back and we'll start doing some more analysis. We'll work on some questions from the text. So let's think of a way to draw a picture for this. So I'm going to draw 4 circles. Why 4 circles? Because I have 4 possible states: 0, 0, 0, 1, 1, 0, and 1, 1. And I'm going to draw a little key down here. And I'm going to say the way I'm labeling these states is with the value of Q1 followed by the value of Q0. Yes, the next state outputs are definitely based on the present states as well as the input. So if your flip-flops happen to be set to a 1 and a 0 and your input is 0, when the clock ticks, this is telling you that first flip-flop will change to a 0, the second one will change to a 1. And now we're in this state that we call 0, 1. So let me draw a representation of 4 possible states. And the way I place these on the page is random. But this state corresponds to Q1 equals 0, Q0 equals 0. This state corresponds to Q1 equals 0, Q0 equals 1. This state corresponds to where both of these are 1, and so on. And I'm going to draw an arrow from a state. And on this arrow, I'm going to list the value of x, my input. And I'm going to make what's called a state diagram. And we can make this directly from the table. So suppose we're in state 0, 0, and our input is a 0. Our next state is going to be 0, 0. So I'm going to draw an arrow from here right back to itself, and I'm going to label that 0. If we're in state 0, 0 and our input is a 1, our next state is 0, 1. So if I'm in state 0, 0 and I input a 1, I'm going to go to state 0, 1. And we're going to do this for all 8 rows of our state transition table. So if we're in state 0, 1 and our input is 0, we go to state 1, 0. So 0, 1 with an input of 0, we go to state 1, 0. If our state is 0, 1 and our input is 1, we go to state 1, 1. So 0, 1 with an input of 1, we go to state 1, 1. 1, 0 with a 0 input goes to 0, 1. So state 1, 0, input of 0, goes back to 0, 1. 1, 0 with an input of 1 also goes to state 0, 1. So we have another arrow here. And then the last two possibilities, if we're in state 1, 1 and our input is 0, we go to state 0, 1. So if our input is 0, we go to state 0, 1. And state 1, 1 with an input of 1, we go to state 0, 1. So 0, 1 is a popular state. Okay, but this diagram makes it easier to see how our system changes state. So suppose you start in state 0. If your input's 0, you just stay here forever. Once your input becomes 1, you come to this state. And if your input stays a 1, you're going to pop over here and pop back and pop over here and pop back. But if we're in this state and your input is a 0, then we're going to pop to this state and back and pop to this state and back. And in fact, once we're in this state, whether our input is a 1 or a 0, we're going to pop back here. And once we're in this state, whether our input is a 1 or a 0, we're going to pop back here. So it gives us a visual representation of how we change from one state to another. Alright, the last thing I'm going to do on this diagram is I'm going to add the output. And I notice that the output only depends on the state. It does not depend on the input. Right? The output is 1 when you're in state 0, 1, whether your input is a 0 or a 1. Output is 1, output is 1, and it's 0 everywhere else. So this is called a Moore machine. A Moore machine, output depends only on the state, not on the inputs. The inputs control what state you go into after the clock ticks, but if you're in state 1, we know your output is a 1. If you're in state 1, 0, we know your output is a 0, regardless of your input. So this is called a Moore machine. And with a Moore machine, I can represent the output by just drawing it underneath the name of the state. So I could say here, if you're in state 0, 0, what's your output? It's 0. 0, 1, your output's 1, and everything else, your output is 0. Or possibly someone sticking their tongue out. I don't know. So there's a state diagram. Okay, we went from this circuit with, you know, weird gates and wirings and all that kind of stuff to this thing that has nothing to do with digital logic anymore. Okay, it's an abstract representation of how a system changes states. All right, so let's take a 5-minute break. We'll come back, we'll do a bunch more examples of this and try to nail down this process, and then you can work on homework questions for this, and we'll make more and more sense out of this over time. Alright, so I'll be back in about 5 minutes.